Hello students, this is Ms. Nielsen and this is your chapter 3.5 lecture on nutrient cycles. You want to follow along with your lecture notes, and this one section in the textbook gets its own lecture because nutrient cycles are a bit of a bear. There's quite a lot to them. So we'll go ahead and get started. So nutrient cycles, so just so you know, they're also called biogeochemical cycles. And when I first heard that word, I thought that can't be a word, that's like everything. But they're the natural processes that involve the flow of nutrients from the non-living environment into the living environment and then back again. So that whole flow of matter and energy that we talked about in the last lecture, it's going to come into play now specifically as we start to look at nutrients. So nutrient cycles involve the one-way flow of energy and then the recycling of the elements. So we're going to go step through them one by one. Before we can talk really about nutrient cycles and how they cycle, you really need to think about where are they located. And we talk about various spheres on planet Earth. So there's the hydrosphere, which is all of the water. And the hydrosphere, of course, we think mainly the largest one, of course, is the oceans, but you're also talking all the other places where we have water on the planet, which includes the atmospheric water. There's the atmosphere then, which is pretty self-explanatory. That's going to be all the gases in the atmosphere and everything else that might be up there. The lithosphere, which is litho means rock, and so that's going to be the Earth's crust and the soil and sediment. Then the biosphere, which is going to cross all those boundaries. We have organisms that live in the rock. We have organisms that live in the hydrosphere, the atmosphere. So that kind of crosses over all the other boundaries. And then the cycling, these flows between one and the next. So we're going to start with the water cycle, and I know you've had water cycle probably going way back into elementary school, but and I'm just going to scan down each of these. There's a few that are worth pointing out that are ones that students can sometimes get confused with. The first one is transpiration. It's a lot like evaporation in that it is an evaporative process, but in the case of transpiration, you're specifically talking about the water that comes out of leaves. And so leaves it's basically the water that is pulled up through the roots from the soil, comes out the leaves through the transpiration process. Another one that students can get confused is the difference between infiltration and percolation. Infiltration is getting the water back into the soil. Percolation is the movement of that water through the soil. And then the term aquifer just means any underground water storage reservoir. It's not like a big underground cave. It can be, but normally aquifers are just saturated areas underneath Earth's surface where all of the pore spaces in the soil or rock are filled with water. That's considered an aquifer. And if you were drilling a well, you would need to drill down to that level, and your well would then fill with water at the top of that, from the top of that aquifer on down. So this is just a simplified little picture, and I'll let you look at that on your own time. They're showing you the transpiration step number 2 right there. It's a little bit hard to see on your notes, but you see the water cycle there. And one of the things that you need to realize is that humans have altered this, and that we remove a lot of water for our own purposes, and we end up then putting it back into the water cycle. So again, just as a review, the similarity and differences between transpiration and evaporation. Transpiration, they both involve changing water into water vapor, so going from liquid to gas. And then again, transpiration very specifically is referring to what happens on the surface of leaves. Evaporation is an abiotic process, transpiration, biotic process. And then for the next one, to put those in the right order, percolation, precipitation, and infiltration, you would need to get the precipitation down on the ground first, and then infiltrate it, get that water into the ground, and then percolation, move that water through the ground. So as you start to apply the water cycle to different systems on Earth, what would happen then if you then cut down a rainforest, which we know happens on Earth? How is that going to actually change the rainfall in a region? And you might be like, well, should cutting down trees affect the rainfall? And the answer is yes, it will. Transpiration is actually a pretty significant process. If you walk into a forest with a humidity sensor, which we have at the school, if you go out from an open field into a forest, your humidity in that forest goes up. And it's because of all the transpiration happening of the leaves on the trees in that forest. So if you cut down a large number of trees, like an entire rainforest, you can actually lose a lot of your water vapor in your air. And then that can in turn reduce rainfall. So the role of water, and again, some of this might seem obvious, but there's actually, like, when you really start to think about it, it drives everything to the point where when we look for life on other planets, the first thing we look for is liquid water. So all of it. So it's like where you have water, you're going to have organisms. If you're lacking water, organisms are going to have a hard time surviving. Aquatic ecosystems, it's literally the matrix in which all of the life exists. Flows of water, it's actually a major way that we transport heat on planet Earth from the equator where most of the heat is received up to the pole. So we have ocean circulation and we have atmospheric circulation. And since water has a high heat capacity, we actually, you can store a lot of energy in that water when it moves around. And then again, we need water for a biotic organism. We need water for all of our life systems too, agriculture, industry, etc. I forget the number on it, but a huge percent of the world's population lives within very close proximity to a major water source. What are we doing to the water cycle? So we take large amounts out of water diversion from lakes, from aquifers. We convert wetlands, we drain them and build over them. We have modified the surface of Earth quite a bit. We clear vegetation, which, as we mentioned in the previous few slides ago, that can change the amount of transpiration, water vapor going into the air, but it can also do things like increase runoff. So instead of as much water infiltrating into the ground, more of it runs off. Same thing if we pave over ground. And then, of course, we're modifying the water quality. We have, nutrients through like fertilizer runoff. We put chemicals in the water. So there's various things we do that can then, impact the quality of the water that we have. And, we are actually, because of climate change, because of the excess heating on planet Earth now, because of all of the greenhouse gases that we put in the atmosphere, we are driving a more energetic water cycle than we've had in the past. And we're seeing that play out in all kinds of ways, which we'll talk about in our climate change unit. So carbon has, of course, it's the basis of life. It's a building block of all organic molecules. It's the currency of energy exchange. So we talked a little bit about photosynthesis and chemosynthesis in the last lecture. And it's stored in those organic compounds. It's also a greenhouse gas, so it's going to trap heat near the Earth's surface. It kind of runs our thermostat. A certain amount of carbon dioxide is good. Too much carbon dioxide, as you know, can drive excess heating of the atmosphere, which can then drive too much climate change. So what are the processes? There's photosynthesis, and we've already talked about that one. That's also known as carbon fixation. And anytime you see the word fixation, it means you're changing that nutrient into a form that plants can use. Movement through the food web, and movement between oceans and the atmosphere, and aerobic respiration. So I think carbon is the most complicated cycle because there's a lot of different moving pieces to it. What makes it a bit easier is that I think you've probably been studying parts of the carbon cycle for a lot of your careers and your years through school. So a few things I'll point out, moving it into rocks and sediments. And so we have a lot of carbon in the oceans and the plankton, marine critters. When they die, that carbon can settle, the carbon that makes them up can settle to the bottom of the ocean, and eventually you can make rock out of that. It's called limestone, and sometimes it has fossils, sometimes the fossils are too small to see, but there's an awful lot of it. Most of Florida is made out of limestone. In fact, large parts of Kentucky, it's a pretty common rock on planet Earth. Fossil fuel formation. So when you compress organic matter, in particular plants, over long periods of time, you can form things like oil, coal, natural gas, etc. And then combustion. If you burn it, those fossil fuels, you're going to put that carbon back in the atmosphere. So here's kind of well, it's simplified. It could be even simpler maybe. I added the volcano because I'm like, that's actually a pretty big process. Volcanoes put out quite a lot of carbon dioxide. And all of these things go into play. And I think one of the things that maybe your earlier years in school tend to ignore is the role of the oceans in all of this. The oceans cover 2/3 of planet Earth. And I'm not saying this just because I have a degree in oceanography, but there's an awful lot of what happens on Earth going on in the oceans. And as we think about what puts carbon into the atmosphere and what takes it out, yes, trees take carbon out of the atmosphere, but the oceans being so vast, the plankton in the oceans also take an awful lot of carbon out of the atmosphere. And of course, that will become important later on, because if that carbon then goes into the oceans, it can lead to something like ocean acidification. So sources and sinks, and there's people who study climate and acidity in the oceans, et cetera, who are going to spend an awful lot of time saying, okay, where are these nutrients and where do they go from one place to another? So as far as atmospheric carbon goes, we have a lot of sources for it. We have respiration, plants and animals letting out carbon, combustion, burning of fossil fuels, release from the ocean. So just the way oceans can take up that carbon, they can also release that carbon back into the atmosphere. There's a diffusion process that goes on and an equilibrium that can happen there. Eruption from volcanoes, like I mentioned before, I left it off this picture. And then decomposition, as things break down after they die, a lot of that carbon goes back up in the atmosphere. So you don't always bury that carbon and make fossil fuels out of, say, dinosaurs millions of years later. Most of what happens to the carbon, most of the carbon when organisms die, is that it is actually re-released. So what takes it out of that's an awfully long list. What takes it out of the atmosphere? Photosynthesis, also known again as fixation, and then dissolving it in the oceans. So, and realize the photosynthesis is going on in both the oceans and by land plants. Dissolving in the oceans, we're talking about a non-biotic way that you can literally dissolve in the oceans and release from oceans in an abiotic way. So again, what are humans doing? And you've heard this before, and you'll probably hear it throughout the class. We were burning lots of fossil fuels, which then put it back into the into the atmosphere. And then on top of it, we are cutting down, doing a lot of deforestation on the planet, which of course is going to reduce the amount of carbon being pulled out of the atmosphere. Those are the two largest causes of the increase in carbon in the atmosphere over the past century and a half. This flux picture, you could stare at this for a long time, but I know scientists who work on these things for a living, and just showing the things in red are human inputs to the carbon cycle, trying to get a handle on what those numbers are, both the red ones and the yellow ones, and even like the size of the reservoir, that the numbers in white is how much is in the reservoir, is a really hard job. We can't do it perfectly. So the best we can do is take our best guesses as to what those fluxes are in our atmosphere. So that was a long time on carbon cycle. Let's go to the nitrogen cycle. This one is a simpler cycle. However, I find it to be more difficult because the vocabulary gets kind of rough on this one. Everything sounds kind of similar. So first off, what's the major reservoir for nitrogen on planet Earth? It is our atmosphere. Our atmosphere is 78% nitrogen, and that's in the form of nitrogen gas. So nitrogen is needed by all living things. It's the N of DNA and proteins. So there's a problem though, in that nitrogen gas in the atmosphere, that N2 molecule, if you look in the lower left of your screen down here, that's a triple bond. That is a super strong bond, okay? That bond is not gonna be broken easily. So it's not easy to get nitrogen into living matter then, because our largest reservoir of it is actually inaccessible as it stands. We can breathe in nitrogen, but we don't utilize that nitrogen we breathe in. So we can't, that's not how organisms get it. So there's gonna have to be a process then to convert that nitrogen into forms that we can uptake. So what are those processes? It's called fixation. So you have to convert that nitrogen gas into something else. And that something else is ammonium. So what can do that? It turns out bacteria in the soil can do that. So, and blue-green algae, that's an anaerobic process. So you find these in the soil itself. There are certain plants like legumes that actually facilitate this by having little nodules in their root systems that host that bacteria. This little picture off to the right shows those little nodules. And I've grown legumes to help fix nitrogen in my soil because I like to garden, and my soils are nitrogen poor because they are in our Pacific Northwest. So you can also fix it by lightning, but I don't know how big a process that is. I think what the little bacteria in the soil do a lot more. So once you've got the nitrogen fixed, you can also convert it to other forms like nitrite and nitrates, which is another way that plants like to uptake that nitrogen. And again, that uptake means that, so whenever you talk about fixing, you're changing it into a form that's usable. And then you think about uptake, that's how you're getting it into the biological system. So ammonification then, in order to be a cycle then, you're gonna have to go back. So decomposers can actually reconvert that nitrate back into ammonium. And then denitrification. I told you there was a lot of vocabulary. So denitrification then, it goes back to the nitrogen gas. And so that completes the cycle. And again, all of this, the whole nitrogen cycle is being driven by bacteria. So when you think, we often think of bacteria as being bad. We use a lot of antibacterial, everything, wipes, soaps, etc. But bacteria is actually really necessary for our cycles on planet Earth, in particular the nitrogen cycle. So once it's converted back to nitrogen gas, it can return to the atmosphere. So here's that cycle again, and you have a version of this in your textbook. But if you look at the picture closely, notice it says bacteria, nitrogen fixing bacteria, denitrifying bacteria, nitrogen fixing bacteria in the soil, nitrifying bacteria. So there's bacteria. When you think about this cycle, think bacteria are what is driving all of it, because for us and we're lucky that there's bacteria there to do it, because for us as humans, we don't have a way to take that nitrogen out of the air and convert it to a form we can use. So just as a review then, a form of nitrogen that can be used by most organisms, that can't be used by most organisms, that is atmospheric nitrogen, all right? We cannot use it. A form that can be used is ammonium or nitrates. So those can be uptaken by plants. And then why are legume plants really good for getting that usable nitrogen is that they host the nitrogen fixing bacteria in those little root nodules. So it's really good to plant legumes in your yard if you want to replenish and put nitrogen back in your soil. And then what are the 3 types of bacteria? So I was like hammering the bacteria thing, but there's 3 different types going on. The nitrogen fixing bacteria pull it out of the atmosphere. The nitrifying bacteria change it into nitrate compounds, which is the way that a lot of plants like to use it. And then the denitrifying bacteria complete the cycle and put that nitrogen back in the atmosphere. So 3 different kinds of bacteria go on with the nitrogen cycle. Fertilizers. So what do we do? Because we can't always plant, beans in our yard. There is Fritz Haber during World War I developed a process to convert atmospheric nitrogen into ammonia to make inorganic nitrate fertilizers. This started the Green Revolution, which is not the environmental movement. The Green Revolution was a way that we could all of a sudden turn not very productive soils into productive soils by creating these fertilizers. But before you think Fritz Haber was a big hero and that he did a wonderful thing, what happened here was good, but he was also his purpose to splitting the nitrogen molecule and turning it to ammonium was to actually make bombs during World War I for the German army. So for Germany. And then he went on to create things like mustard gas and whatnot. So his kind of like Garrett Hardin, there's not all good for what he did for the environmental or for planet Earth. Okay, so again, for each of these cycles, we're gonna be looking at what humans are doing to it. We emit nitric oxide, which leads to air pollution and acid rain. We emit nitrous oxide. It's a potent greenhouse gas and also depletes the ozone in the stratosphere. And then we put a lot of fertilizers on our farmland, and that's good for making the soils more productive, and that's why we do it. It's bad, however, in that if those fertilizers run off into the local water bodies, it can cause eutrophication. Phosphorus cycle, my favorite cycle. And it's my favorite cycle because it's the easiest cycle. So I talked to you about Venus the other day in class, and phosphine is not a naturally occurring, it's PO3. Well, that's because on planet Earth, as far as we know, all of our systems on planet Earth use only one form of phosphorus, and it's phosphate, PO4, everything, PO4 phosphate. So it's a really easy cycle because the other thing that's nice about phosphorus is that you don't find it in the atmosphere. It is strictly goes from the rock into the rock can weather down, goes into the soil, plants can take it up out of the soil, and then we can use that phosphorus in our systems. So we use it, again, think about what it's needed for living things like DNA, ATP, phospholipids, bones, tooth enamel. We use phosphorus for a lot of things. And it can also, if there's not enough of it in the soil, it can be a limiting factor for growth. So how are we impacting the phosphorus cycle? We mine large quantities of it because we do need it for fertilizers. We also use phosphorus in our detergents. If you cut down forests, you're reducing the availability of phosphate. And then again, if we put too much fertilizers on the ground or they don't soak into the ground well enough, it can cause runoff. And then also raising livestock, birds put out a lot of phosphorus in their excrement. Chicken farms and whatnot, that runoff can get into local water bodies and cause eutrophication. Okay, sulfur cycle, we're not really going to talk about. If you notice, your notes are lacking anything on sulfur cycle, and that's because they took it out of the AP CED, the guide for us. But I did want to mention it because it is an important cycle, and I don't always trust that what they take out that they won't actually test you on. But when you think sulfur cycle, think mainly what we're doing with it is we put a lot in the atmosphere through the burning of coal and through smelting processes. The other major source in our atmosphere is volcanoes, and that's a big, if you've ever been anywhere volcanic, volcanic, which hopefully you have been because you live in Washington State, you know that rotten egg smell, that sulfur smell anytime you're near any active volcanoes. Go to Yellowstone and you'll know what I'm talking about. But we need that sulfur also in our life systems. And there's also quite a bit of sulfur in seawater. It's a fairly common element on planet Earth. And so it's one of the important nutrients in the cycles also. So this is just a simpler form. I just wanted to show you also, so it's an amino acid, so we do need it. It is a nutrient that's needed for life. But just realize that bacteria drive the sulfur cycle too. So it's bacteria in the soil that can reduce it or oxidize it so that it can be used by organisms. What are our human influences? I already mentioned these, but fossil fuel burning. Smelting, turns out most of our metals are naturally occurring on Earth as sulfides, meaning if we want zinc on Earth, it occurs as zinc sulfide. If we want that zinc, we need to take the sulfur out, which means that that's a chemical process. And for a lot of years, we would just let that sulfur off into the atmosphere. And then that once it's up there, it can cause acid rain. And we'll be learning more about the sulfur cycle in our air pollution unit. All right, so finally, kind of like a synthesis slide. Major reservoirs, and then how do we get them into organisms? So water, their major reservoir is the hydrosphere. How do they get it? Through the soil, otherwise known as part of the lithosphere. Carbon, it makes up all major reservoir. It's going to be all the biomass on planet Earth. And there is a lot in rocks and whatnot, but when you're talking the cycling, when it's in rocks, it's locked up for millions of years. So the major source for carbon is going to be the biomass. How do we uptake it? The atmosphere, so through photosynthesis. Nitrogen, major reservoir, 78% of our atmosphere is nitrogen gas, but how do we take it up? Through the soil. Sulfur, major source is rock. It's a very common element on planet Earth, and a lot of our rocks contain sulfur. So how do plants take it up? The soil. And then phosphorus, once again, we find it in rocks. So how do plants take it up? The soil. So major takeaway from this slide is that except for carbon, all of our nutrients we take up through the soil, which means that if we're not treating our soils well and we're depleting them or letting them wash away or blow away or whatever it is, we can really impact our ability to keep these cycles going and being able to raise enough food, etc. So final slide. And is that, again, the only nutrient that's taken up through the air is carbon. Everything else comes through the soil. So we're going to be doing a whole unit on soils, but it's, I think, a little appreciated reservoir on planet Earth is our soil. And I think we have not treated it well for decades, and that has led to some issues. So that ends the lecture for chapter 3, and we'll see you guys. Make sure you've got your notes filled out, and we'll see you guys back in class.